So in our previous episode, we looked at Einstein's paper of 1905, and we saw that there were 9 sections and we reached up to 6th section. And in 6 sections, he has developed a theory for electromagnetic radiation, and the main driving point which he has mentioned in the opening paragraph was a symmetry between material bodies and electromagnetic radiation. He wanted to treat them at par. If material bodies allow for discrete energy packets located in atoms and molecules only, then electromagnetic radiation should also do that. That was the driving force. And then he calculates all varieties of entropies and expressions and all those things, and shows that the entropy of this electromagnetic radiation, form of that, and entropy of a gas of material particles, molecules, they have the same kind of expressions. And in place of number of gas molecules, you have a certain quantity which we discussed. So energy is, total energy is distributed in those separate locations, which he calls quanta or energy packets or photons. We now call it photons. And then we saw that, okay, if we assume that all these quanta are identical, then the energy should be some constant times mu. Now, the remaining 3 sections, 7, 8, 9. He takes some experimental data, and from that experimental data, he supports the theory. So let us look at those 3 sections also, and then we will conclude how it is related to photoelectric effect. Okay, so here is that last part of section 6. From section 1 to 6, he is constructing a theory of monochromatic radiation, and finally finds that it can be regarded as a discontinuous medium consisting of energy quanta of magnitude h nu. Now, the next task, once the theory is already developed, now the next task is to investigate whether the laws of emission and transformation of light are also of such nature, right? So what he has shown in section 1 to 6, that monochromatic radiation itself is can be regarded as a discrete quanta of energy h nu. Now what he is saying, that when this radiation falls on matter, and then it causes emission of electrons or something, or the energy is of light is transformed from one nature to other nature, or one way to other way, can that also be interpreted in terms of these such quanta? And then he takes 3 examples. Section 7 is Stokes' rule. What is the Stokes' rule? It says that if you have some substance which absorbs light and then emits light, photoluminescence, what happens if it absorbs a light of frequency nu and then it re-emits light, then that frequency will be always lower than the original frequency of the radiation. That is called Stokes' law, right? So there he says that, okay, very fine, yes, why not? Why not? If nu1 is the original frequency of light, and if we consider that it consists of energy quanta h nu1, which is absorbed, then maybe part of it is dissipated in this way or that way, and then the remaining is emitted by the material of frequency nu2, radiation of frequency nu2, the energy quantum h nu2 must be smaller than h nu1, that is conservation of energy. You cannot create more energy unless that material itself is creating energy. So if a quantum of h nu1 is going and then a quantum of h nu2 is coming out, h nu2 must be smaller than or equal to. So this is Stokes' law, well known Stokes' law is okay with our theory. we can understand it with our theory of photons. And then comes this section 8, which says concerning the emission of cathode rays through the illumination of solid bodies. Now comes photoelectric effect. All right. So now here he is mentioning the usual conception that energy of light is continuously distributed over the space throughout which it propagates encounters very serious difficulties when one attempts to explain the photoelectric phenomena, as has been pointed out in her Lenard's pioneering paper. So he talks of this Lenard paper. This paper here, the reference is given here, 1902, and that's the only paper that he refers to. Okay, so photoelectric effect paper just comes as an example. Stokes' rule was one for photoluminescence. This is the second example, and the theory that he has developed in terms of energy quanta, he tries to apply it here. So here he applies his description of light. The simplest way to imagine this is that light quantum delivers its entire energy to a single electron, and then rest everyone knows that if this h nu, this is that h nu. So this h nu energy is given to the electron by this energy quantum, and then this is the work function, this capital P is the work function. This is the energy that electron has to spend if it wants to come out of that attraction of this metal, the bondings and everything. So that's it. So this much is the maximum kinetic energy available, assuming that nothing is dissipated in thermal energy and so on. So that's it. So that is how now he says that this is stopping potential business, that if you apply some potential there and just enough to prevent this loss of electricity by the body, that means just to prevent that emission, then this stopping potential has to be like this. And then he says that, okay, this the numbers match very well and so on and so forth, a result agreeing in order of magnitude with those of Herr Lenard. Okay. Now, this is also important because Lenard does not talk of the relation between the stopping potential or maximum kinetic energy and frequency. But once this equation is established, from the equation Einstein says that if the derived formula is correct, then this is that stopping potential thing, when represented in Cartesian coordinates as a function of the frequency of incident light, must be a straight line, which slope is independent of nature of the emitting. These things we teach in our classrooms, but then Einstein is predicting this, not that Einstein is explaining it, because the data was not available. And therefore, from the equation, Einstein is predicting this stopping potential versus frequency curve. Okay, so that's all. If the energy of quantum is independent of blah, 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 all those things he sees. And here he explains that this maximum kinetic energy is independent of intensity. He says that if each energy quantum of the incident light, independently of everything else, delivers its energy to electrons, then the velocity distribution of the ejected electrons will be independent of the intensity of the incident light, right? So on the other hand, the number of electrons leaving the body will, if other conditions are kept constant, be proportional to the intensity of the incident light. So these things he explains based on the thought, or the based on the result that the light can be regarded as photons. And then comes the last section, that is 9th section, photoelectric effect over, concerning the ionization of gases by ultraviolet light. So this is something else, and he again says that our photon picture will be okay. You can explain all those observations also. So you have seen this entire paper, the 9 sections of Einstein's paper, and now you can see the context. This Einstein's work is not on photoelectric effect as such. The work is to look for the symmetry in materials and radiations. If the materials can be described by separate energy quanta localized at certain locations, which are molecules there, then for light also one should have those kind of descriptions. So that was the driving force. And then using thermodynamics, using the concept of entropy, comparing the thermodynamics of material gas and this radiation, he comes out with that result that okay, radiation can also be regarded as a collection of separate energy quanta, right? And then he takes photoelectric effect as example which supports this theory, and then he very easily shows that okay, the mechanism is that you have this emitter, you have this emitter or cathode, and then light falls. When light falls, what is falling? The energy quanta are falling, and they are interacting with electrons, and the model is one photon, one electron in one go. Most of the events will be like this. In that model, the energy given by this radiation to any of these electrons will be just h. The energy given to a single electron in a single event will be just h nu. Once the energy is received, then this electron will not keep this energy for a long time with it. Either it will come out or it will share with the fellow electrons and the lattice. So one electron, one photon, this is the energy given. And then it may share with the other electrons or ions or the lattice or this metal as a whole, and whatever is left with it, it is possible that it is still enough so that it can come out, because coming out is not trivial. It's electron of that metal, so it is a bonding, and if it tries to come out, the electron will be pulled by this metal. Then breaking that bonding will need energy. So that energy is your work function. That energy is called work function. The minimum energy which is required just to overcome this bonding with this metal, that is work function. So that energy is spent there. So h nu is received, and then this work function, this much of energy is used in coming out, and in between it may also share with the other entities here, and therefore the kinetic energy with which it comes out could be less than this or at best this. This will be the upper limit, and therefore this is your half mv square maximum. You will have electrons which will have energy less than this, kinetic energy less than this, but this is a maximum. So, and to stop this current, if you use this as a cathode, and then you have an anode, emitter and collector, you can call it collector. The electrons are getting collected here, and then you have a circuit. These electrons are recycled. You may have some potential differences and all that, like this. So this way you can have the circuit. This can be made positive, this can be made negative, and if you make this as positive, okay, so let me make this longer. If you make this as positive, this is, let us say, at zero potential, and this is at some positive potential, then the electric field is towards right, and it will repel this electron. It will apply force on electron towards the left. So whatever is trying to come out, it will be retarded. And the minimum voltage, if this is at 0 volt and this is at plus V volt, then the minimum value of this needed to stop all these electrons is the same as which stops this maximum kinetic energy electron, and therefore you have that E times V naught equal to half mv square max, and therefore this E times V naught is hv minus 5. This is your textbook stuff. This is your textbook stuff. This is what we teach. This is what we study. This is called Einstein equation. And then he says that, okay, Leonard had shown that this velocity distribution of these electrons does not depend on the intensity. Very good, very nice. There is no term of intensity here. So it does not depend. So the experimental observations are consistent. That it shows. And then Leonard has also shown that if there is a current and you increase the intensity, right, then the current also increases proportionately. So that is also fine. If you increase the intensity, that means you are sending more photons per unit area per unit time. So more electrons will have the opportunity to receive that energy, and therefore more electrons will come out and the current will increase. So those things he explains. The Leonard's observations he explains. But that's all. That's all he has to the data. But then he says that fine, if this is the case, so if someone does an experiment in which he or she uses light of different frequencies, different sources of light, and for each source, each monochromatic source having a single frequency or a single wavelength, finds what is the stopping potential, and therefore collects data on stopping potential as a function of this nu. So there's a table. Then you have this nu, and then you have this V naught. So there's a table. If someone does this experiment, what the person should find. So if this is all correct, then the equation is V naught is equal to h by E times nu minus pi by E. And if this is plotted on the horizontal axis, this is plotted on the vertical axis, it's something like y equal to mx plus c. And you know that is a straight line with this at the slope, m at the slope, and plus c as the intercept on the y-axis. So this is negative intercept here. So if you plot this V naught here and this nu here, it should be of this kind. It should be of this kind. And here, the slope here, okay? You know what is slope? Tan theta. Tan theta means if you go some distance here, increase this nu by certain amount, then you find how much is this V naught is increased. So this is increase in nu, this is increase in V naught, and this divided by this is tan theta in this figure, and that is called slope. So slope of this curve should be h by v. Universal constant, independent of what material is here, what is the work function, and everything, anything that you think of, it is independent of that. So you can use different materials. For one material, you collect all those data, plot. Now you change the material. Work function is changed. Again, collect the data and plot. What you will see? Same slope. This intercept may be different. This intercept may be different. So you may have this kind of picture or this kind of picture. So this is material 1, this is material 2, this is material 3. Slopes are identical, they do not change, but the intercept will change, and intercept should be related to this work function. So this is the prediction, right? This is the prediction. This is prediction. No one had done this experiment so far, 1905. No, that's all about it. That's all about Einstein's work on so-called photoelectric effect, okay, which earned him the Nobel Prize. But then, do you think This was very drastic, this was a revolutionary concept, and once it was published, it could bring a strong storm in the whole community, physics community. Nothing like that. People just ignored it. People just ignored it because the wave theory of light was so well established. Experiments, all those experiments, interference, diffraction, polarization, and then theory, Maxwell's theory, which so wonderfully predicted that electromagnetic waves should have this speed c, 3 into 10 to the power 8 meter per second, matched so well with the speed of light which was measured by that time. So this wave theory was so well established, anything which is different from that and again talks of radiation as separate quanta, separate units, and in between no energy, that was just dumped, right? So Einstein was ignored, his work was ignored, physicists criticized it, did not pay much attention to it and all that. That all went on for almost a decade. And then comes another great experimentalist, Robert Millikan, who performed wonderful experiments on photoelectric effect and had a very, very crucial role in establishing Einstein as his model as having some sense in it, and finally earned Nobel Prize for him. Unfortunately, in our textbook description of photoelectric effect, we do talk of Leonard, we do talk of Hallwachs, Hertz, Einstein, but we forget the contribution of Robert Millikan. So next episode will be on Robert Millikan.